I would like to do another projectile motion example, and we'll make this one considerably more difficult. Let's say you are playing softball and you are a shortstop. You make a play, and now you've got to throw this ball, and you're going to throw the ball over this way to try and make a play at first base. First base over here is going to try to catch the ball, and we want to figure out the speed of our throw. What we do know is that we have trained hard and we have a lot of power, and we can throw this ball pretty comfortably at 15 degrees so that we get minimal arc and we can catch it as quickly as possible. We're going to say we are throwing from a height of 1.8 meters, and we are going to catch it at a height of 1 meter. So we are no longer catching at the same height that we're throwing. We would like to know how far that is. From the shortstop to first base can vary a little bit depending on where you are between second and third, but 20 meters is actually pretty close to the middle of that range. So let's see what we can do. I'm going to start off by making a table. X initial, X final, V initial, V final, acceleration, and time. I'm going to do this for the X direction and do this for the Y direction. This is a bit of a strange problem because I'm looking for that initial speed, and that's kind of tough. It's unusual. My X initial, I need to pick a spot that I'm going to call my origin, and I'm going to say right here, directly underneath the ball, is going to be my origin. So here's my Y-axis, here's my X-axis, which means my initial X position is 0. My final X position is going to be 20 meters. My initial velocities, I'm going to skip for just a moment. My acceleration in X is 0. My time I don't know. If I don't know my time in X, I don't know my time in Y, but I do know that these two are going to be the same value as each other. That's my tied together concept for projectile motion. My initial height, I'm starting at 1.8 meters. I'm ending at 1 meter. And my acceleration is going to be -10 meters per second squared. I'm going to take a second and figure out these velocities. I want to look at this launch velocity and pretend for a moment that I do know my diagonal. So right here horizontally, I'm going to get a V initial X, and it's going to be equal to V initial, which I don't know, times the cosine of 15. I'm going to get over here a V initial Y, and that's going to be equal to a V that I don't know, times the sine of 15 degrees. So I'm going to put those values in, even though they are kind of incomplete. V initial, cos 15, my acceleration is 0, so that velocity is going to stay the same the whole way through. And then over here, V initial times the sine of 15 degrees. Last time I was able to say my V final was going to be negative V initial because I was ending at the same height that I started on. I don't have that situation anymore, so I'm going to leave that as a question mark. This is kind of my basic setup, and then I want to make sure I have my equations in there. So there are my equations. I just copy pasted them. I use them enough. Here we go. I would like to start solving this thing. I said I was going to try and keep a line right down the middle of this and do my x and y separately that way. I'll give it a shot. See how that goes. I'm looking for v initial. It's the only thing in red, but that's what I'm looking for. I'm going to start maybe with my x direction and see how it goes. In my x direction, my acceleration is 0, and again, if my acceleration is 0, my equations 2 and 3 simplify to those which are true but not useful. So as soon as my acceleration is 0, I know I would like to use equation 1. Here's equation 1. And I can cross off that one and that one, but it still leaves me with x final equals v initial, which was v initial cos 15 degrees times the time, which I also don't know. I have two unknowns in this equation, and that's kind of a problem. I'm not going to be able to do much with that. So I'm going to switch over and look at the y direction stuff. Because I used equation 1 in x, I would like to start by using equation 1 in y. It might not be the right move, but it's a high percentage play. Alright, I can plug in nothing. I can cross off nothing. So I'm going to just write this equation the way that I actually have this. V initial times sine of 15 times time plus a half times I acceleration time squared. I have two equations with two unknowns. I'm going to have to actually do something with this. So I need to solve this system of two equations with two unknowns, and there's not a particularly clean way to do it. I'm going to take this equation over here because it's the simpler one and solve it for one variable, then plug that into the other and hope that that works out okay. I think what I would like to do is solve this one for v initial equals so that I can only have to plug it in the one spot. I know it's going to be kind of a pain, and that means I'm going to end up with having to solve this thing twice. But let's see. So over here, if I solve for v initial, I'm going to get v initial equals x final over t cos 15 degrees. I'm going to take all of that and boldly cross my horizontal line and plug it in here for v initial. Let's see where that goes. Y final is y initial plus v initial. That was my v initial times sine 15 degrees. What? Fix this. Times t I'm going to get plus half a t squared. A little bit ugly, but we're going to be okay. I can cross off a t here with a t here. That's pretty nice. I get a y final equals y initial plus, I've got a sine divided by a cosine, and I know that's a tangent. Don't have to have it, so I could write this as sine 15 over cos 15, but being that I'm going to have to plug in a bunch of values into a calculator or, computer or whatever anyway, I'm going to try and keep that as simple as I can and write that as tangent of 15 plus half a t squared. I'm solving for t. All these other things are known quantities, and that's pretty nice. So this time I will show you a bit more of the algebra. So I'm going to subtract off y initial on both sides. I'm going to subtract off x final tan 15 on both sides. So my left side becomes y final minus y initial minus x final times tangent of 15 degrees equals, and my right side is half acceleration times time squared, and I know that's my acceleration in the y direction. I guess I can label that. That was an acceleration in y. I'm solving for t, so I'm going to multiply by 2. That's going to cross that off. Then I'm going to divide by a. And then I've got t squared, so I'm going to square root. And square root over here. And that leaves me with 2 times y final minus y initial minus x final tan 15 all over the acceleration in y, all under a square root, equals t. And I'm going to plug in some values. Y final, and I can just go right back to my table. I'm even going to take this table and copy paste it into the space where I'm working so that I don't have to keep going back and forth. Two times y final is 1 meter. Minus y initial minus x final times the tangent of 15 degrees all divided by my y acceleration, all under a square root. And my t works out to be 1.11 seconds. I'm going to put that in for my time. Now I would like to know what my v initial is. So I can do that in the x or in the y direction. But along the way I made this equation back here in blue. And that said, I can find my V initial if I know these other values, and now I do. So my x final, which was 20 meters, divided by the time times the cosine of 15 degrees, and my V initial works out to be 18.65 meters per second, which is a little more than 40 miles an hour. It's almost 42 miles an hour, which is actually a very reasonable throwing speed. A good thrower is still going to throw somewhere in the 50 mile per hour range. So this isn't some outlandish number, but it is a complete example of a projectile motion problem.